Okay, so we're going to continue talking about conditional distributions today, and then we're going to get to independence, which is a really important topic for random variables. So last time we defined the conditional PMF or PDF, and we defined the conditional PMF or PDF. So given we had some random variables x and y, the conditional PMF or PDF of x given y is going to be the joint PMF or PDF at x and y divided by the marginal for y, and we can always flip x and y. And so this is the conditional PMF or PDF of, in this case, x, given that we observe y is some value little y, and it's the conditional PMF at little x. And we said that this thing, x given y is little y, is, we can think of it as a univariate random variable. So it has, say, a PMF or PDF, and it will have an expectation. And so we can define conditional expectation, and this is going to be defined pretty much in the way we think it would be defined, is that if I have some function g, which is just a real valued function, r to r, then the expected value, so before I've looked at the expected value of g of x, but now we can look at the expected value of g of x given y is equal to little y. And before we had calculated the expected value of g of x as the integral g of x times f of x, but now we multiply by f of x given y, but we still integrate with respect to x. So this is the continuous case, and of course in the discrete case, it would be the sum over x, g of x, f of x given y, and so this is for discrete. And this is just very straightforwardly an analogy. If we recall in the univariate case, the expected value of g of x, which is by our law of the unconscious statistician, was g of x, f of x, dx, say in the continuous case. But now we just replace f of x with the conditional distribution x given y, right? And so it is exactly just the expected value of what I was just calling this univariate random variable up here. If there is some univariate random variable, call it z, that represents x given y is equal to little y, then if we take the expected value, which is kind of like a version of x, it's a version of x given information about y, the expected value of that z would exactly follow the formulas we have here. So it's pretty simple. We can look at an example. So we can continue the example from last time, where we talked about the shifted exponential. And so we said that in this case we had y given x is some value little x, and I could say is distributed exp for exponential, the rate parameter was 1, and I can say the shift, which is a new parameter, is whatever my little x value is. And what we saw in that example was that f of y given x had the formula e to the x minus y as long as 0 less than x less than y. So this is our previous example. Either of those are okay ways to think about it. And I could ask for this, say, what is the expected value of this random variable y given x is equal to little x? And we can calculate this now with our formula. So this is basically asking the question, we could get the marginal distribution of y, and you could ask the expected value of y. But you could also say, what is the distribution of y if I know x is this value, little x here? And then given that, what would I expect y to be? And we just have a formula here. It's just y times f of y given x. And we integrate dy. And we can fill in the actual details. My limits, y goes from x to infinity, according to these limits here. Y and f of y given x is e to the x minus y, and I integrate with respect to y. So this is an integral. I'm not going to solve this integral. If you do integration by parts, you can solve this one. We let u be y and dv be e to the negative y. We should get our answer. Why do I have to include the x? Well, obviously, my x should just come out, right? So what we get at the end of the day, if we solve this, is we get ... integration by parts. We're going to get 1 plus x. So I'll leave that as an exercise for you to do. And you can verify that if I do integration by parts, that way I get 1 plus x. It's just an integral problem, so it's a Calc 2 problem. But that is what I wanted to calculate, which was the expected value of y given x. Okay. And so if we can define conditional expectation, we can also define conditional variance, right? And this is going to kind of feel very similar. So let's write definition, conditional variance. Since variance is just defined in terms of expectation, we can just replace all of the expected value formulas with the conditional expected value formulas. So the variance of y, say, given x is little x, or I could say x given y is little y, follows the following formula. Expected value, we're going to take y. We're now going to subtract off the conditional expectation. So normally you just subtract off expected value of y, but now we're subtracting off the expected value of y given x is little x. You look at that thing squared, but now this outer expectation is also conditioned on x being equal to little x. So we've just replaced both of the expected values in the normal variance formula. We've replaced them with conditional expected value. And so let's look. If we don't want to kind of use this complicated formula, there is, of course, a shortcut formula. And I'm sure you can imagine what it's going to be, that the variance of y given x is little x. We can take the expected value of y squared given x is little x minus the square of expected value of y given x is little x. We square that thing, right? So again, this is the same shortcut formula, but we're just replacing conditional expectation, or replacing the normal expectation with the conditional expectation. So it's pretty straightforward. It's just bootstrapping off of our previous theorems. I'm not going to prove any of these because they're basically very trivial given our previous formula. And we can continue our example, right? So again, continuing our example above, I could instead ask for the variance of y given x is little x. And our shortcut formula says this is the expected value of y squared given x is little x minus the expected value of y given x is little x squared from the previous example, if you've done the integration by parts, this should give you 1 plus x. So if you square that, it's 1 plus x squared. And now we just have to calculate the expected value of y squared given x. And so this is, of course, we place, now it's y squared times f of y given x and dy. And so expanding this out, the limits go from x to infinity, y squared, e to the x minus y dy. And again, I'm going to say integration by parts. I'll leave this as an exercise to you. We're going to get x squared plus 2x plus 2. And so altogether, if we wanted our variance of y given x, little x, it's x squared plus 2x plus 2 minus 1 plus x squared. Leaves us with just 1, right? We expand out that square. So in this case, the conditional expectation, which is 1 plus x, does depend on x, but the variance actually is independent of x, and that can happen. So that's a nice little example, and it gives you some practice with integration by parts, which is always good for the soul. So, okay, so we've talked about conditional distributions, and we can do all the kind of similar things we want with the univariate distribution with conditional distributions. All we're doing is replacing the PDF or the PMF with the conditional PDF or PMF. And one thing that we did back talking about events was we talked about independence. And so independence is a natural follow-on from when we talk about conditioning things. So we can now give a formal definition of what it means for random variables to be independent. So we talked about independence for events way back, and now we can talk about independence for random variables, right? For events, our definition was that the probability of AB was the probability of A times the probability of B. That was our definition of independence. And for random variables, if I have two random variables, x and y, what we're going to say is that if I pick any two events, A and B, if the probability x is in A and y is in B is just the probability x is in A times the probability y is in B, then x independent of y. So this is our definition. So this is our definition of independence of random variables. And this is really just bootstrapping off of our definition of independence for events. So it bootstraps off independence for events using events. We could just look at inverse image of A under x and the inverse image of B under y. Those are two events, and basically random variables are independent if those events are independent for all possible A and B. So not just any A and B you choose, but if for any possible A and B I choose, those two events, x inverse A and y inverse B, are independent in the sense of events, then we say x and y are independent. Or we can equivalently, that's using the definition above here, which is we can do this kind of factorization, where we can distribute probability over things in this way. So that's the formal definition. It's not always the most useful way to think about independence. So maybe the more useful way is this immediate theorem. And the theorem is called the Factorization Theorem. So let's call it a lemma. It's a quick little theorem. It says it's called a factorization lemma. Okay? And the factorization lemma says x is independent of y if and only if. So it's an equivalent way of finding independence. If and only if I take my joint CDF, and if I can factor my joint CDF into the product of the marginal CDFs. Or x is independent of y if and only if my joint PMF or PDF factors into the joint PMFs, or the marginal PMFs or PDFs. So the factorization theorem says I don't have to check this very complicated thing for all possible events. All I got to do is find my CDF, my joint CDF, and my marginal CDFs, or my joint PMF or PDF, and my marginal PMF or PDFs. And if I can factor them, if the joint is just the product of the marginals, then we have independence. So it's a very useful theorem, and practically is often the easiest way to establish independence. So a nice little follow-on fact from this. So I'm going to state that without proof. The follow-on fact, that's not very legible, fact, is if x is independent of y, I can look at, say, my conditional PMF or PDF, f of y given x, right? F of y given x, by definition, is the joint over the marginal for x. And if they're independent, I can factor my joint PMF or PDF as the product, and lo and behold, I'll get cancellation. And similarly, f of x given y is the same thing as f of x. So if I have independent random variables, then the condition, if I condition y on x, that doesn't change. That's just the same thing. Look at the marginal. Or if I condition x on y, that's just looking at the marginal of x. So we saw very similar facts for events, and kind of similar rules hold for random variables also. Okay, so let's look at an example of checking independence. So here's going to be our example. It's going to be a discrete problem. So I'm just going to write out the joint PMF. So x can take on values of 10 or 20, and y can take on values of 1, 2, or 3. And I'm just going to write out my values for my joint PMF. Okay, so let's write out some values. So I can check that this sums to 1, 2 tenths, 2 tenths, 4 tenths, 5 tenths, and 5 tenths, so that the whole sum is 1. So this is a valid joint PMF. So this is, let's just write that, joint PMF. And the question I want to answer here is x independent of y? So how do I check that? Well, I could get the marginals and see if the joint is the product of the marginals for every possible values. So let's look at marginals. Okay. So the marginal of x, so I can write x, and I can write f of x. So the marginal for x. X can take on two possible values, 10 or 20. And I get the marginal for x by just summing over the margins. So I sum 1/5 plus 1/5 plus 1/10. So that should give me 1/2. And similarly, if I sum 3/10 plus 1/10 plus 1/10, that gives me 1/2 also. So it looks like x is has a just simple distribution, either 10 or 20, 1/2 probability for each. I can also look at the marginal for y. Look at y against f of y. This can take on three values, 1, 2, or 3. And I just sum across the rows of this table. So, so let's see if I sum across the rows. If x is, or if for y being 1, I get 1/10 plus 1/10. is 1/5. If y is 2, 1/5 plus 1/10 is 3/10. And if y is 3, I get 1/5 plus 3/10, which is 1/2, right? So that's the marginal for y. And the question is it true that fx times f of y, the marginal for x times the marginal of y, for all possible values of x and y, is it true that it's always equal to, if I take the product of those, that will give me the joint distribution. So, for example, if I look at f of 10, so x is 10 and y is 3, that will be 1/2 times 1/2. And is that equal to the joint, 10/3? 10/3 is 1/5. So actually it's not equal to 1/5, which is f. So it's the joint at 10/3. And so this tells me, so x, I could say, independent with a cross through it, x is not independent of y. Okay, that's a real simple example, checking independence and just using that theorem there. Okay, so this factorization theorem is very useful. We actually don't even need to show what the marginals are. So the corollary, or the kind of follow-on, is that x is going to be independent of y if and only if I can write the joint PMF or PDF as some h of x times some g of y. So some function, so function only of x, and g is a function only of y. So they don't even have to necessarily be the marginal of x and the marginal of y. They could be. That would be satisfy the theorem. I just have to show I can separate out the joint into the product of something involving x and something involving y. And I could make those the marginals that are clever enough, but I don't even need to actually find the marginals, which could involve integration that I don't want to do. As an example of why this is a really nice theorem, if I look at, so let's just come up with a really nasty joint PDF. So here's my nasty PDF. 1/384, x squared, y to the 4th, e to the negative y minus x over 2. And this is for x bigger than 0 and y bigger than 0. Okay. I claim this is a joint PMF, or PDF, joint PDF. Okay. Now, if I want to find the marginals, I have to do some integration. I would have to integrate out x and integrate out y. I don't want to do that, because that takes time. And what I want to do is really quickly answer the question, which is x independent of y? Well, it looks like I can write my joint f of x, y as the product of two functions. So here are the two functions. The first is 1/384, x squared, e to the negative x over 2. And the second, I can just pull out this term, and this part, is y to the 4th, e to the negative y. So we all agree that we can write it that way. And so I've factored it into some function of x only, and this is some function of y only. So above I call this h of x, and I call this g of y. It doesn't really matter. But because I can do that, x is independent of y. More to the point, this h of x and g of y are up to some scalar multiple are the marginals. We have to find the correct normalizing constant, but up to the scalar factor, those are the marginals. Okay, so that's really nice because I don't actually have to do that integration to find if they're independent, and that will save me a lot of time. So we talked about conditional bivariate expectation, conditional expectation. So what does independence say about expectation? So here's the powerful theorem that we all want. Theorem. Expected value for independent random variables. Okay. If x is independent of y, then the expected value g1 of x times g2 of y. So g1 and g2 are just some real valued functions, whatever I want. They go r to r. And if I take the expected value of some function of x times some function of y, I can factor this. I can distribute my expected value over the product. And that is super nice, because we've all wanted to do that. And generally that doesn't work, but it does work for independent random variables. So for independent random variables, I can distribute over products and kind of the bivariate expected value. Proof of this, again, is just basically following from properties of summation integration and that factorization theorem we just talked about. So let's do it for the continuous case, the discrete case, you replace the integrals with sums. If I look at the expected value of g1x times g2y, we know that the definition of bivariate expectation, this is g1 of x, g2 of y, f of x comma y, dx dy. It's a double integral. But my factorization theorem says I can factor f of x comma y into f of x, f of y. All right, into the marginal of x and the marginal of y. And now we can separate these two integrals. This is the integral of g1x fx dx multiplied by the integral g2y f of y dy. And that, of course, is given our definition of univariate expectation. It's just expected value of g1 of x times the expected value of g2 of y. So pretty simple proof, nice little theorem, very useful. So let's look at an example of applying that. Example. I'm going to say both x and y are distributed exponential with a rate parameter 1. And I'm going to say x is independent y. And we can look at expected value of x squared y. Now we know how to do this, but our theorem says that this can be factored. And so really it's the expected value of x squared times the expected value of y. And if you recall, for exponential distributions, if you go back and look, if you have an exponential distribution with rate parameter lambda, the expected value let's say if I have some z that's exponential lambda, the expected value of z is 1 over lambda, and the expected value of z squared is 2 over lambda squared. So this works out to be 2 times 1. Okay? So super nice. So the expected value is just 2. And that is a real quick way of calculating it using our factorization of expected value. Other things that turn out really nice when we have independence include the moment generating function. So we've seen these MGFs before. And so here is our little lemma. Short, that's not well written, lemma. Short little fact. And this is about MGFs of independent. Okay. And the theorem says, or the lemma says, that if x is independent of y, then if I look at the MGF of x plus y, so MGF of x plus y at some value t, MGF is your value to a number t, right? That is just the product of the MGF of x at t times the MGF of y at t. And this follows directly from the factorization theorem for expected values, right? So the proof is, real short. The proof is that MGF of x plus y at t is the expected value of e to the t x plus y, x plus y. Properties of exponents say this is the expected value of e to the tx, e to the ty. And factorization says this is the expected value of e to the tx, e to the ty. And that is, of course, mx of t times my of t. So for independent, sums of independent random variables, the moment-generating function is just products. So this is going to play, hopefully by the end of the course we'll get to talking about the central limit theorem. This plays a lot in the central limit theorem. An average is basically a sum of random variables. And so the sum of a bunch of independent things, like in the central limit theorem, is going to be the product. The MGF is just going to be the product. And that will help us a lot. Hopefully we can get to that proof. It'll be a lot of fun. Okay, we can look at an example of this. So this gives us a nice little immediate theorem about normal random variables. So here's the example. If x is normal mu sigma squared, and y is distributed normal, let's say gamma tau squared, so some different things, and x is independent of y, then if we look at m of x plus y, the moment-generating function of x plus y, we know from this theorem it's mx of t times my of t. And we know, if we go back and we look at the moment-generating function for a normal random variable, this is exponential of, so the MGF of x is exp of mu t plus sigma squared t squared over 2. And the MGF of y is correspondingly now gamma t plus tau squared t squared. Let's not mess this up. Tau squared t squared over 2. And we can combine some terms. You could write this, I'll let you do the algebra, as mu plus gamma t plus sigma squared plus tau squared t squared over 2. And so if I call mu plus gamma a and sigma squared plus tau squared b, this is exponential of at plus bt squared over 2. And this is the MGF has the exact form of a normal AB random variable. If you look at the formula for an MGF of normal with parameters A as the mean and variance B, that's what the MGF is. And so what this says is that x plus y has the MGF of an AB random variable. So it is distributed AB, i.e. x plus y, the sum of two normals, is normal, where the mean is the sum of the means and the variance is the sum of the variance. This is true, and we have to remember x is independent of y. If x is not independent of y, that does not work. But if they're independent, all we have to do is sum the parameters of normals. So sums of normals are also normal, and we get the new parameters for the normals by just summing the parameters. So normal distribution is your friend. It's a very nice distribution. It has nice properties like that. So last time we talked a lot about covariance and correlation. And again, we can talk about what happens when we have independence. Independence is just the great simplifier. It makes everything nice. So let's talk about covariance or correlation for independent. So covariance or correlation is supposed to measure linear dependence between things. Our intuition is that things are independent. That means they're not related. And so if two things are independent, they should not be correlated. And that theorem says that if x is independent of y, then covariance of x and y, or the correlation, whichever you want, of x and y, is 0. And we can prove this real simply, right? So notice that the covariance of x and y, we can use our shortcut formula from last time, expected value of the product xy minus expected value of x times expected value of y. And if x and y are dependent, I can factor this expected value as product x times y. And lo and behold, oops, I've written this in a weird order, but lo and behold, everything cancels. And notice that correlation between x and y is proportional to the covariance between x and y, right? It's just a normalization factor, right? We divide through by the standard deviation, so the square root of the variances. And so certainly if the covariance is 0, the correlation will also be 0. So this is 0 also. Sort of like that. Okay. That's a very useful theorem. If things are independent, then, so this is an arrow going that way, independence implies covariance is 0. Converse is not true. Is generally, there's one case where it's true, but the converse is generally not true. That is, if we know that the correlation or covariance between x and y is 0, we don't know they are independent. Unless you know something else. And we'll talk about that maybe next time. But there's only one kind of special case for this work. Generally, if the correlation is 0, it could be dependent still. They won't be linearly dependent, so correlation measures linear dependence. But they could have some other kind of non-linear dependence. So the example, simplest example, is that if x is normal 0, 1, and y is x squared, right? These things are definitely dependent. Y is just the square of x. If I know x, I know exactly what y is. However, they're not linearly dependent. They're dependent through a squared relationship. So the correlation is going to be 0. If I look at the correlation of x and y, this is, let's look at the covariance because it's simpler. Covariance of x and y, this is the covariance of x and x squared. And the shortcut formula says this is the expected value of x times x squared minus the expected value of x squared times the expected value of x, right? This is what our shortcut formula is. And so this is the expected value of x cubed minus the expected value of x times the expected value of x squared. Now, a fact is that for a standard normal distribution, the rth moment is 0 for odd r. The odd moments are 0 if the mean is 0. Certainly we know that for x is normal 0, 1, the first moment, that is this thing, is 0. And this thing I'm going to claim is also 0, and so the whole thing is 0. All right? And because 3 is not a number, the third moment x cubed is 0. So what this shows is that the covariance is 0, but x and y are definitely dependent, just not linearly. So knowing the covariance or correlation of 0 doesn't tell us they're independent. X is definitely not independent of Y. As a quick proof of this fact here, if I look at the expected value of x to the r, this is the integral of x to the r f of x dx, right? And r is odd. The PDF of a normal 0, 1, or any normal centering 0 looks like this. It is an even function, symmetric around 0. So this is even. X to an odd power is odd, and so the whole thing is odd. And if I integrate it across all possible values of r, I get 0 because it's integrating an odd function over a symmetric integral. So as we saw before, integral of odd function over symmetric interval. That's a cute little fact we can show. Okay, but that's the classic example showing that correlation or covariance being 0 does not imply independence. The other way is true. If they're independent, covariance correlation are 0. Okay, so other things that we had for events, and now we can talk about, because we have definition of conditional random variables, not just conditional events, we can look at things like Bayes' theorem. So Bayes' theorem for random variables. And so if you recall, for events, we had that Bayes' theorem said that the probability of A given B is the probability of B given A times the probability of A over the probability of B. Right? Now, I can say that the conditional PMF or PDF, conditional distribution of y given x, for example, I can pull a similar kind of thing. It's f of x given y, f of y over f of x. So this is true. As long as this thing is bigger than 0, right? And that's true of all conditional distributions. We can never have the thing we're conditioning on cannot have probability 0, otherwise we run into problems. What else can we do? We can look at the law of total probability. And this Bayes' theorem is just a rearrangement. I mean, we can do a quick proof of it, I suppose, but this is just basically a rearrangement of our formulas. Here, I'll do a real quick one-line proof, right? We know that f of y given x is f of xy over f of y, or equivalently, f of xy is equal to f of y given x times f of y, right? And just rearranging the formula. And equivalently, it's f of x given y times f of y, right? So those are the kind of two facts. I can equate each side and then solve back, and I'll get what I have above here, right? This says that f of y given x times f of y is f of x given y times f of whoops, am I writing this wrong, right? Whoops, this y should be an x, shouldn't it? This first y should be an x. There you go. So f of y given x times f of x is the same thing, f of x given y times f of y. Or I can just move my fx to the other side. I'll move that down to the basement there, and I get what I want. So it's just a rearrangement of all the formulas, right? Okay. Law of total probability for events. So let's again say, recall that for events, the law of total probability said that if I partition my sample space into some set thing c sub I, say I goes 1 to n, then probability of seeing A is the sum over I of the probability of A given c sub I times the probability of c sub I. And we can get something similar for random variables. So the theorem for random variables says that if I want to, so let's first do for discrete random variables, if I want to get, say, f of y, this is the sum over x times f of y given x times f of x. And for continuous, if I want the marginal of y, I can instead integrate. I can say it's the integral of y given x fx dx. So this is a kind of similar law of total probability. So these laws should hopefully look very familiar because they're very similar to what we saw for events. Now we're just doing it for random variables. And we can look at a real quick proof of this. It won't be too surprising, right? The kind of proof of this is that, let's say, f of y given x is the joint xy over fx, or equivalently, we can say fxy is f of y given x times fx, and so that's fact 1. Fact 2, we know this, that the marginal, we can get the marginal if we integrate out x from the joint. And so combining 1 and 2, we get that f of y is, if I integrate, I'm going to replace fxy with f of y given x, fx, and I iterate with x. That kind of gives me a law of total probability. And the discrete case looks very familiar. Replace integrals with sums. Okay, let's look at some examples, in particular of this law of total probability. It allows us to do some real fun problems. It specifically allows us to, now I can specify the marginal, the marginal x and the conditional y given x, and I can get the marginal of y. So here's a classic example of using this. So assume that y, if I know the value of x is some little x, y given x has a Poisson distribution at x, with parameter x, right? So given x is little x, y has a Poisson x. And so I'm going to specify the conditional y given x, and then I'm going to specify the marginal is that x marginally has an exponential distribution with parameter lambda. And the question is, what is the distribution of y? So this is used all the time in so-called Bayesian statistics. This is exactly the games you kind of play. So this is the fundamental basis of it. Okay, so here's the problem. Y given x is Poisson, x is exponential. What's the marginal? What is y distributed as? Our formula from above, our law of total probability, says I can get fy. What I'm going to do is take y given x, multiply by x, and I'm going to integrate with respect to x. And so let's plug in. So we have an integral. Y given x is Poisson with parameter x. So the parameter now is x. So Poisson would be, instead of lambda to the y, it's x to the y, e to the negative, instead of e to the negative lambda, it's e to the negative x, and over y factorial. So this is a Poisson x. And then the marginal is a exponential lambda. Integrate with respect to x. And my limits, what are my limits on x? X is an exponential, so it goes 0 to infinity. So now we just got an integral to solve. And it's an integral with respect to x. So anything that doesn't depend on x can just come out, right? I got a y factorial, doesn't depend on x. And I've got a lambda that doesn't depend on x. And so I'm left over with this integral 0 to infinity, x to the y, e to the negative lambda plus yes, lambda plus 1 x. I can combine my e to the x here, this one, with this one, right? So e to the negative lambda plus 1 x. And of course, I'm integrating with respect to dx. Now, what you might not immediately notice is that this starts to look like a gamma PDF. So the trick here is going to be I'm going to make it into a gamma PDF by multiplying by the right constants, and then that integral is going to go away. I'm going to have to solve integrals. And I don't like solving integrals, so let's make that one go away. Recall here that if z is gamma alpha beta, the PDF f of z, let's say, it's supposed to be a z, is beta to the alpha over gamma to the alpha, z to the alpha minus 1, e to the negative beta z. So what I'm going to have to identify here is that it looks like a gamma in x, so this y is alpha minus 1. Beta is lambda plus 1. So I think that it's gamma, or it's basically a gamma. Alpha is then y plus 1, and beta is lambda plus 1. What I'm missing out front is I'm missing the normalizing constants out front here. I'm missing this. So what I can do is I'm going to multiply and divide. So by those constants. So let's bring this all the way down here. So I got a lambda, got a y factorial. I'm going to multiply by gamma of alpha, which is y plus 1, divided by beta, which is what? Lambda plus 1, to the alpha, which is alpha, which is y plus 1, right? There we go. Okay. And then, so I multiply by that, which means inside my integral, I can multiply by the reverse, which is lambda plus 1 to the y plus 1 over gamma of y plus 1. And then I'm left here with, go back, with just x to the, x to the y, e to the negative lambda plus 1, x dx, and this thing will all integrate to 0, integrate to 1. Because it's just the integral of a gamma PDF, and so I'm just going to be left with these constants out front. Okay, so let's bring down the integral goes to 1. What am I left with? Lambda. Gamma of y plus 1. Y is an integer, right? So y given x is Poisson. So y better be an integer. So it is gamma of y plus 1 is y factorial. If you go back and look at our facts about gamma function, over y factorial, lambda plus 1 to the y plus 1. Ooh, that's nice. We get some cancellation. So it's gamma over, I'm sorry, lambda over lambda plus 1 to the y plus 1. So this is the marginal of y, and this is some negative binomial distribution, if you happen to care. But it doesn't really matter. We got the marginal distribution of y. We got the marginal distribution of y just knowing the conditional of y given x and the marginal of x. Okay, let's look at another example along the same lines. So that was a nice little example because it was actually mixing two different types of distribution. It was mixing a continuous x and a discrete y. So the next example let's look at here is a similar kind of thing. So it is where x given y is binomial with parameter y and some p. So p is just some number in 0 to 1 here. Okay. So what am I saying? Given y is some little value y. So what I'm going to do is I first, well, let's specify the distribution of y. Y is Poisson with some parameter lambda. Okay, so here's the experiment. First, draw a number y from a Poisson distribution. Maybe the number is 5. I'm going to then do a binomial experiment or 5 Bernoulli experiments and count the number of successes. So first I get y, and then I do a binomial with the number of trials is equal to the value of y, and the probability of success is some value p, which is just fixed. And the question we can answer is, what is the distribution of x? So what the hell is a distribution? What am I going to see if I do this experiment? Or first I draw something from Poisson, and then I do a binomial experiment with that many trials, my binomial experiment with certain value of probability says p. How many, what's the count going to look like? How many successes am I going to see in this binomial if the number of trials in my binomial is also random? So the problems start to get real fun this way. Okay, so let's look at this. So I want f of x, which is, in this case, x is discrete. So this is just the PMF, or the probability x is equal to little x, right? And I can get this by summing, right? I can get this marginal by my law of total probability. For the discrete case is I can take f of y given x multiplied by f of y, and then marginalize out y. Sum of this is the law. So this is a law of total probability for a discrete case. Okay. So let's write out what this is. We know that the PMF of x given y, so x given y is binomial. And so sum, y goes 0 to infinity. Right, y is Poisson, so the support of y is anywhere from 0 to infinity. This is f of y given x is the binomial with per n being equal to y. So it's y given, choose x, p to the x, 1 minus p to the y minus x. And then I have to multiply by f of y, and y is Poisson. So with Poisson with parameter lambda, it's lambda to the y, e to the negative lambda over y factorial. And let's continue on here. what am I going to do? So a couple notes here. We can use a little trick here that says y, we've seen this before, y choose x is the same thing, or y choose x times 1 over y factorial is, so we're going to take that term and that term, and if we do this out, right, this is y factorial over x factorial y minus x factorial. And then we have a 1 over y factorial. And so what we get left with is 1 over x factorial y minus x factorial. And that x factorial, as it were, doesn't depend on y, so it can always come out of our sum. So let's pull out everything out of our sum. So the x factorial comes out. P of the x doesn't depend on y. E to the negative lambda doesn't depend on y. And we can also factor out a lambda to the x. If I do that, I need to multiply by a lambda to the negative x. So what are we left with? The y choose x over y factorial. The only thing that's left is y minus x factorial. We still have a 1 minus p to the y minus x. And instead of lambda to the y, since I need to account for the lambda to the x, it's going to be lambda to the y minus x. Okay. Those are all equivalent. So now we've got our whole sum in terms of y minus x. 1 over y minus x factorial, 1 minus p to the y minus x, lambda to the y minus x. And so that looks promising. And what we're going to do now is we're going to kind of abuse this summation notation here. So what are we going to do? We could write this. So let's see. Over x factorial, p to the x, e to the negative lambda, lambda to the x. We could re-index our sum. Y goes 0 to infinity. And what we get is y factorial 1 minus p to the y lambda to the y. All right, so we can just change our sum to let's back up here. The reason we can do that is our original sum really should have started at x, right? Okay. Let's back up and change that. Our original sum should start at x because if we can't have the situation where x is less than y. I'm sorry, where other way around, right? If we have the situation where y is less than x, that's not going to comport if we go back up and look at the original problem, right? So the original problem here was that, so we draw some y and then we draw x, some y, and then we draw x from a binomial given whatever value we chose for a little y. So x here can be anywhere from 0, and it can be at most y. Or equivalently, y has to be bigger than or equal to x, right? If y is not bigger than or equal to x, we get a problem, because then we'd have more successes than we have trials. So our sum here, the support, y goes bigger than or equal to x. And so y is bigger than or equal to x. So now when we re-index, we can change it from sum starting at x to just sum starting at 0. Okay, and so now these are equivalent. And this, we've seen this before, is just e to the 1 minus p times lambda, right? So I could actually factor out the y, and this comes from the fact that we know that if we look at the sum, y goes 0 to infinity of a to the y, this is just e to the a, right? That's the general fact we know, Taylor series expansion of e to the a. In this case, this thing is a. So what we get left with altogether here is we get an x factorial in the basement. We get a p and a lambda to the x. We get an e to the negative lambda and an e to the 1 minus p times lambda. Of course, we can cancel some of this, because we can cancel this e to the negative lambda with the 1 here. And so we get p lambda to the x, e to the negative p lambda over x factorial. This is a Poisson distribution with parameter lambda p, or p lambda. So what does that mean? X has a Poisson with lambda p. So the experiment was draw y Poisson and then draw x from a binomial with number of trials from that Poisson. Turns out we just get another Poisson where the rate is the original rate times the probability of success of the original experiment. So that's a kind of cute little result there. You can calculate, for example, that the expected value of x is just, for instance, lambda p. So if we draw for Poisson, get some number y, and then we do a binomial experiment with that y many draws in our binomial experiment, we will get a another Poisson, and we're going to expect to have lambda times the percentage of the draws in that binomial as our parameter there. Okay, so this is some nice, real fun problems now. This really gets into the heart of kind of Bayesian statistics here. Last thing we're gonna start to look at today, and we'll see how far we get, is we're gonna look at what's called iterated expectation. So here's the theorem. Iterated expectation. And I'm just going to write down the theorem, and then we're going to talk about it. If x and y are random variables, then I can calculate the expected value of x as the expected value of the expected value of x given y. I'm going to write it like this. Okay. That's the theorem. So this is called iterated expectation, because I'm going to iterate. I'm going to do expectation twice. If I want to get the expected value of x, I can take the expected value of x given y, and then take the expected value with respect to y of that quantity. So let's first talk about what the terms in this thing mean. first of all, we've seen the expected value of x given y is little y. Okay? This, for each value little y, this produces a number. And so it's, in some way, we could think of it as some function g of y. You give me y, you give me little y here, I give you the expected value of x given little y. So it gives me a function. So g here is a function, takes in y, spits out this expected value, which is just another number. So g is a function. It's a weird function. It's a function that takes in y and spits out expected value of x given the random variable y is equal to that little value. And we know how to take the expected value, say, of, if I want to take the expected value of g of, g of y, right? For some arbitrary function g, I know how to take that expected value. But I could use, as my arbitrary function g, I could use this function g, which is just some real valued function. And so this is denoted when we do this as the expected value of x given y. So now these are both capital letters, bold. We don't say it's equal to little y. It's like I'm plugging my random variable y back into this thing. So this thing is a random variable. So let's back up here. Let's not look at the expected value. Let's look at, not the expected value. We know how to do a transformation of y, right? So if I take, so let's back up first, right? So I can get this function, let's call it g. It's the expected value of x given y is some little value. For each little value y, I get this value. Call it g. I could transform y with this function. So I could basically plug y back in for that little y. So you might be tempted to write something like expected value of x given y is equal to y, right? If I were to kind of plug my random variable back in there. But that's kind of cumbersome. So what we do is we denote it this way. We denote it as the expected value of x given y, where x and y are both random variables. This quantity is a random variable. Which random variable is it? It's the random variable we get when we take y and we plug it into g. So we're defining x, expected value of x given y, as transformed version of y, transformed by this function g, where g is defined this way. So it seems a bit circular, but it's not. It gives us a valid random variable, expected value of x given y. So if both of them are capital letters, that's a random variable. Whereas this thing, expected value of x given y is equal to little y, is just a number. So this thing is a random variable. It is a random variable. So since this is a random variable, we can get its expectation. And we could say, what is the expected value of this thing? So in my theorem, I write that. Expected value of e of x given y, and then I put another expected value on the outside. It's the expected value of this random variable. It is a random variable, and it is specifically, that is a function of y, so, or a transformation of y. So specifically, e of x bar y is a transformed version of y. And so when I take this expected value, really I'm taking it with respect to y. And so what this is equal to is, right, I would look at g of y, which is this thing. This is g of capital Y. And I'd multiply by the marginal distribution of y, and then grade respect to y, just like a normal function, right? So when I write out, and I write subscript y here just to remind me that I'm multiplying by the PDF of y. So the theorem Okay, so it all seems a bit confusing. It's a bit circular. Think about it. The theorem says that if I do this thing, first I take the expected value of x given y, and then I do an iterated expected value with respect to y on the outside. That just gives me the expected value of x. And we can look at a proof of why this is true. So let's look at a proof in the continuous case. So the proof in the continuous case says that the expected value of x is x times fx dx. And I know that I can write fx as if I take the joint and I integrate out y, this gives me fx. So we can write it like this. And I can just rearrange, or I can use my theorem to say that the marginal fxy is the same thing as y given x times fx. So this thing is the same as fx comma y. That's my joint. And now I'm just going to kind of bring things out. So I can write this as a double integral x f of y given x just like this. Cool. What do I want to do? I probably want to do this the other way. So actually, let's back up here. Let's do this with respect to y. Let's say this is y given x times f of... Oh, I'm sorry, that was right. Let's back up here. Oh boy, let's think about this. Which way do we want it? We want to say that this is fxy. We want to say it's x given y because we really want these integrals. Okay, so that's correct. So we can write this as x given y times f of y. So let's write it that way. This will be the result we want. X given y times f of y. And, okay, right, so let's set e of x, integral of fx dx. I can expand out fx as if I marginalize out y from the joint f of x comma y. I can write the joint as x comma y as fx given y times fy. And now I'm just going to rearrange the order of these things, right? And so let's see, which order do I want these in? I can write this as the integral of x times f of x given y. Let's bring the dx in here. So let's do the x integral first, and then I can say f of y dy. This thing here is precisely right, so this thing here is precisely for a given value of y, it's expected is the conditional expectation of x given y is equal to little y. And so this is this, f of y dy, which is precisely what we had written up. It's the expected value with respect to y, right? We get f of y times this thing, which is what our formula says. Okay, so this connects our iterated expectation, which should just give us back expected value of x. So the takeaway to remember here from this theorem is that expected value of x given y is some little value y is a number, and the expected value of x given y is given y, close bracket, is a random variable. Okay, so let's stop there. We'll come back next time and we'll look at some examples of this.